Welcome. One of the most important theorems in differential geometry is the fundamental theorem of curves. It tells you that if you have a curvature description of the curve given in terms of a curve in little SON, this Lie algebra of the rotation group, then you have, via these equations, the Frenet equations, you have also a curve in the rotation group SON. And then this describes us then the curve, gives us the curve because the first row gives us the velocity vector, and once you have the velocity vector you have the whole curve. So this is a very beautiful result, and we can look at stability. When does the curve stay bounded? So this is a question I've not seen, but it's a beautiful natural question. If a periodic function k of t, 2 pi periodic function k of t, what happens with the curve? Does it stay bounded or not? And I yesterday just wrote down this theorem which gives the answer in a simple situation where the curvature is just given as a constant plus one, periodic function sine of m of t multiplied with the amplitude, which is not 0. So in this case we see there is stability even only if we have no resonance. It's kind of a nice result, I think, and it's done in 2 dimensions. Maybe I'll say something more about 3 dimensions next time, which is harder. There I looked at the case where the curvature is constant and torsion is a periodic 2 pi periodic function, and I look there at the case when is this bounded or when is it not. And so this is a very interesting question also, and harder than the 2-dimensional case. This is in the quaternions, this is in the complex numbers. So this is commutative, so easy. This is non-commutative already, non-commutative group, and harder. Maybe just as a little bit of culture, this is a old theme in mathematics. Stability is very important in engineering, it's important in mathematics, and I got excited about this as a grad student, and this was kind of one of my Bibles, the book of Moser, Stable and Random Motion, 750, that was the prize when this book came out. This was the Hermann Weyl lectures, and he has talks in length about the Sitnikov problem, which is a beautiful 3-body problem where you have 2 suns, like Alpha Centauri, a double star system, and then you have an Earth going perpendicular to it, which is mathematically accessible and shows that you can have horseshoes embedded, so meaning a chaotic calendar. You can essentially get any, possible, calendar which you want to have. It's a very interesting problem. Moser also in his 78 article mentions this exterior billiard problem, which is very nice, and there was a lot of progress recently. So it depends on the smoothness. So for C0 or C1 curves you can have instability. There are examples, but for higher, I don't know whether it's known for C2, but for higher smoothness C3 I think it's enough. You have Km Tori far away, so it's hard problems. This is a hard implicit function theorem involved. This is the twist map theorem of Moser, which is also described in this book. Not proven in this book, it's too hard. Also, I was once in a seminar of Moser where one of the students was presenting the stability problem of a pendulum. So you have a pendulum. Pendulum is very easy, right? So you have a pendulum. So pendulum is kind of a boring system. It's used for clocks, so it's very boring. It's periodic. It can be solved explicitly using elliptic integrals. I talked once about this and gave a solution actually with Weierstrass elliptic functions, which I think I've never seen before. But it's kind of just relatively boring, but mathematically quite interesting that you have this kind of nice motion on the torus via the Jacobi map. It's very, very beautiful mathematics, classical mathematics. And the question is, if you now kind of shake the table or the the wall on which it is attached. So, or if there's periodic, you know, disturbance through the moon, for example, you have the moon, you know, circling around the Earth, and so this disturbs the gravitational field slightly, very little, but slightly. And the question is, is it enough to shake up the pendulum? And the answer is also here. We have KEM theory, which tells us that we have stability if the perturbation is smooth enough. The perturbation is not smooth, you know, just continuous function, and we know no, there is no result there. We probably don't have stability. So very, very beautiful stability problem. And here we have a stability problem in differential geometry. We have the curvature function, periodic function question, when is the curve bounded or not? And the nice thing is that we can explicitly solve everything in the two-dimensional case, because it's equivalent to a Schrödinger equation, so a time-dependent Schrödinger equation where we have no, and it's just the world is just one point. We have no Laplacian yet, right? So there is just k of t is the Hamiltonian. So that's the general structure of a Schrödinger equation, where this in general is an operator, but in this case it's just a periodic function. And now when you go and solve this, right, you can actually get the integral of the curvature over time. That's what we call in mathematical physics the phase. Method of stationary phase, for example, looks at such integrals. These are action integrals which you have in mathematical physics, which appear often, but they are, you know, not solvable. They are difficult things. So we have, in this case, we have this integral. This is the explicit solution of the curve in terms of an integral which we cannot solve. But we have just to find out whether r of 2 pi is equal to r of 0. And of course we make a Fourier expansion of that. And that's, if you look it up in the books, you get Bessel functions here as coefficients. And then you have these terms, and you can look when is this really kind of this integrate. This is integrate. We can integrate each of these terms. We get this. And so if k minus mn is not 0, never 0, then we have a sum of periodic functions and everything converges nicely, and we have stability. Now, if k minus mn is equal to 0, you can use Hopital. It's a nice exercise to see that this is actually just t, you know, kind of a constant times t, then, and so we have a linear motion here. So if k is a multiple of m. For example, if you take m equal to 1 and k equal to 1, you have instability. You can just look at that. You get this kind of curve which goes to infinity. And the displacement you can explicitly compute. So maybe I'll talk next time about this problem, which is much harder, because you are actually here, you all have a curve in the quaternions, unit quaternions, the unit sphere in the three-dimensional sphere. This is a non-abelian group. It's a non-abelian setup. It's harder. And that's it for today.